Hi, I'm Yavor Litchev, and on behalf of the Stanford Blockchain Club, we are very excited to interview Dr. Boneh today. He is one of the authors of the recent LatticeFold papers titled LatticeFold, a lattice-based folding scheme and its applications to succinct proof systems, and the subsequent paper, LatticeFold Plus, faster, simpler, shorter lattice-based folding for succinct proof systems. Both of the papers are published on ePrint Archive for anyone who is interested in learning more. We believe that such research will further proliferate proving systems, such as zero-knowledge proofs, where you can basically prove a statement is true without revealing why it is true, such as showing that you know the solution to a Sudoku puzzle without revealing the exact solution. This will be extremely helpful for the blockchain ecosystem and ultimately allow for more information to be shared and proven on-chain. We also believe that these papers represent a substantial shift towards cryptography that is post-quantum secure. Without further ado, let's dive into the questions. So, our first question is, can you give us a high-level overview of what folding is in cryptography? What problem does it solve? How does it relate to recursive snarks? And how is it conceptually distinct from zero knowledge? Where does LatticeFold fit in this landscape?
Okay. Yeah. Thanks, Yavor. Thanks for running this and welcome everyone. Looking forward to the conversation. It's a pretty long question, so let me try to unpack it and maybe answer it one piece at a time. So, yeah, you already explained what zero knowledge proofs are. Generally, they're extremely useful in the blockchain space. They're useful for scaling the blockchain. They're useful for privacy applications on the blockchain. Now, the issue is that when you look at traditional zero knowledge proof systems, what we call actually we call snarks that are the things that are actually useful for blockchain systems. Snarks basically stands for succinct proof systems. So they're not just general proof systems, they generate succinct proofs that are short and fast to verify. The problem is if you're trying to prove a very complicated statement, like for example, you want to prove that an Ethereum block is correct, only contains valid transactions, that is a huge statement. It's about 10 billion RISC-V instructions, so it's a very large statement to prove. And it turns out many of the proof systems that we have today, they simply run out of memory when you try to prove such a large system. So the traditional solution to this is what you would expect. Yeah, let's instead of proving the entire block as one monolithic block, let's try to break it into smaller tasks. So we'll break it into chunks and then do a proof of each chunk separately. Yeah, so we might take this big block, 10 billion RISC-V instructions. We might break it into 1,000 smaller sequences of instructions and prove that each one of those sequences ran correctly. So now the prover actually has enough memory to prove each one of those subtasks. The problem is now we end up with, 1,000 proofs, right? One proof per chunk. And then there's this really beautiful idea called recursion, where you can take those 1,000 proofs that you now have, and you can run sort of what's called a second layer prover that proves not that the block is correct, but just proves that those 1,000 proofs that we have are correct. So this is a proof of a proof. It's not just a proof. Yeah. And so we take our block, we break it into chunks, we prove each one of the chunks, and then we prove that the 1,000 chunks that we ended up with, the 1,000 proofs we ended up with, are all valid. And you can imagine actually an even deeper tree. Like we don't have to do all 1,000 proofs at once. Maybe we break it
Mhm.
into sequences of hundreds of proofs. We
Right.
prove that 100 proofs are correct, and now we end up with a smaller number of proofs, and then we prove that those proofs are correct. So we kind of get a large tree or a deeper tree of proofs to do that. Yeah, so that's called a recursive snark because we're kind of applying the snark prover recursively. Now, the problem with recursive snarks is they're somewhat expensive to do, right? If you think about what the prover has to do, when it needs to prove like one chunk of the computation, it has to generate an entire proof that that chunk is correct. And then it has to do a proof that it has to basically run the snark verification algorithm inside of a proof itself, right? It's doing a proof of a proof, meaning that the snark verifier ran correctly. So there's two kind of bottlenecks in this recursion process. A, you have to generate a complete proof, and B, you have to prove that you have to run the snark verifier inside a proof. So you have to prove that the snark verifier ran correctly. And this is kind of where folding comes in. So folding is kind of a more efficient way to do proofs, where the idea, it's really kind of a remarkable idea, that instead of doing recursion, instead of proving that you have a proof, what we do is we take rather than actual doing proofs, what we do is we take two statements that we're trying to prove, for example, two chunks of a computation that we're trying to prove, and we fold it into one chunk. Yeah, so we're kind of taking two statements and we fold them into just prove that so that the result is that we only have to prove one statement that's actually only as big as the original statements. That is why it's called folding, because we're kind of folding two statements into one. And once we've done that, we can just keep iterating, right? We can keep kind of folding more and more and more statements into this accumulated statement. And at the end, we end up with an accumulated statement that we have to prove, and that statement we can prove however we want. Yeah. So that's kind of the idea of folding. You take many statements and you fold them into a single statement, and then you prove that single statement however you want. Now, the benefits of folding are that, first of all, folding is actually much simpler for the prover than actually generating a proof. Yeah, so all you're doing is you're kind of taking two statements and folding them into one, and that turns out to be just a simple kind of linear operation. So the prover is much faster when it does folding as opposed to recursion because it doesn't actually have to generate a proof. It just folds two statements. For the verifier, this turns out to also be much easier. The verifier just has to verify that the folding was done correctly. Yeah, and then again, that's much easier than checking a full snark proof. Yeah, so that's the benefit of folding. You can take your 10 billion instruction block, break them up into small chunks, and then fold all those chunks together into a folded chunk into a single folded chunk that's only as big as one chunk, and then just prove that folded chunk with whatever proof system you want. Yeah. So that's kind of the idea that it allows us to do these proofs faster.
I see, I see. So, thank you very much for that answer. And you kind of went into this a little bit as to the history of folding, but there exist many other folding schemes besides LatticeFold, like, for example, Nova, Hypernova, Protostar. What gap is LatticeFold closing relative to those, specifically with the inclusion of the modulo short integer hardness assumption and the Ajtai commitments, the operations over a small field? And does what kinds of applications would benefit from staying from these cyclotomic rings RQ? So, for example, would this be beneficial to machine learning or something like what is the difference between this folding scheme and the other folding schemes, I guess?
Okay, great, great. So the idea of folding is dates back to 2020, so it's
Mhm.
not too old of an idea.
Mhm.
And it turns out for folding, we need something called linearly homomorphic commitment scheme. Yeah, so if I commit to one value and I commit to another value, I can take those two commitments, add them up, and I'll get a commitment to the sum of the values. Yeah, so we need a linearly homomorphic commitment scheme. Now, there are some actually recent works that say maybe we can fold without linearly homomorphic commitments, but the most efficient folding scheme use linearly homomorphic commitments. Now, the original folding scheme, like you mentioned, Nova, Hypernova, all those other ones, they basically rely on a folding scheme a commitment scheme called Pedersen commitments. Yeah, Pedersen, your listeners can look it up. It's a way to commit to a large amount of data. The commitment is small and the commitment is homomorphic. Yeah. So again, if I commit to two vectors, I can sum up the commitments and I get a commitment to the sum. Uh, so there's two problems actually. It turns out Peterson commitments are somewhat expensive to compute. They require a lot of exponentiations, and that is a little bit slow. That's one issue. And the other issue, which of course many of you know, is because it's based on the discrete log problem, this problem is not secure against a quantum computer. So again, we don't know how realistic the quantum threat is, but we do need to be prepared. And so the question is, are there folding schemes that maybe are faster, and hopefully they will also be secure against the quantum computer. Yeah, and that's kind of where lattices come in. So lattices are kind of the standard solution that we have to the threat of a quantum computer. As you might know, lattices are being used for key exchange on the internet. So we are replacing our pre-quantum key exchange methods with post-quantum key exchange methods based on lattices. They can be used for public key encryption and for other things. And so the question is, can we use them for doing snarks? Can we use them for proofs? Now, it turns out lattices are a little bit difficult to use for actually doing snark systems. So actually, literally kind of doing a monolithic snark turns out to be somewhat difficult with a lattice because we end up with relatively long proofs. The proof systems themselves are somewhat complicated. But it turns out that lattices, surprisingly, are amazingly good at folding, which is kind of the point of our work. As you mentioned, LatticeFold, LatticeFold Plus, and I also want to mention a work by one of my students called Neo. These are kind of the three folding schemes that are out there. Yeah, so what's the benefit? So first of all, by using lattices for folding, there's the hope that the resulting folding system will actually be quantum secure. So we have that benefit. But surprisingly, it turns out when we move to lattices, we don't use Peterson commitments anymore. We're going to use a commitment scheme on lattices. And the commitment scheme, as you mentioned, it's called ITI commitments. Yeah, so ITI commitments are very simple to describe. They're so simple, it's amazing that they're secure. Effectively, when you want to commit to a large vector, what you do is you just generate a random matrix, and actually I should say it's a random rectangular matrix, not square, a random rectangular matrix, and you compute a matrix vector product. Yeah, so you want to commit to your vector. You generate this matrix, you compute this matrix vector product, you end up with a much shorter vector, and that short vector is the commitment to your original vector. Yeah, so you can see you take a large vector, you hit it
Mhm.
with a rectangular matrix, and you end up with a short vector that's your
Mhm.
commitment. That's it. That's the whole commitment scheme. So again, your listeners should probably say, wait a minute. This is too simple. This doesn't sound like a very secure commitment scheme. And in fact, as I described it, it's not secure.
Mhm.
It's possible to open the commitment in two different ways, so the commitment is not binding. But it turns out if you add one more condition, namely that the vector that we are committing to actually has low L2 norm, all of a sudden the scheme becomes committing. Yeah, it's kind of very surprising, but that's kind of how this works. So as long as I'm committing to low L2 norm vectors, it turns out when I give you a commitment to a vector, I can't open the commitment in any other way other than the vector that I committed to begin with. Yeah, which is what we want for a commitment scheme. Yeah, in a commitment scheme, if I commit to a vector, I shouldn't be able to open the commitment in two different ways. This is the binding property. And as I said, as long as a vector is low norm, the scheme seems to be binding. Yeah. So the benefit of this, first of all, is all you're doing is a matrix vector product. Yeah. So it's super duper fast, much faster than Peterson commitments. So all of a sudden, by shifting to lattices, we get much faster, potentially much faster folding schemes. And we also have the benefit that even if you have a quantum computer, it's not clear how you break the binding property of this commitment. So we potentially get both post quantum and efficiency. Okay, so I think the second half of your question was this question of emphasis, like why are
Right,
we
like
using
why that as opposed to like learning with errors and like other like lattice assumptions, I suppose, because there's a variety of them, but why that one specifically?
Yeah. Good. So, right. So let's first of all start with SIS. So, SIS stands for short integer solutions. So
Mm.
the fact that ITI commitments are binding, that is an assumption. We call that assumption the SIS assumption. Effectively, that's what it translates to.
Mhm.
Um, yeah, so it's hard to find short solutions to these linear systems. Um, it turns out that still requires a matrix vector product, which is a quadratic time operation. It's still kind of expensive to compute. And so we have further optimizations. What we can do is rather than working with integers, it turns out we can work in slightly more complicated rings. Yeah,
Mhm.
so this is where cool algebra comes into play. Hopefully, I really encourage all your listeners
Yeah.
to take a modern algebra class. What is it? Stanford, it's Math 110, I think, where you
Yes.
learn about groups and rings and fields. Very important
Mhm.
stuff. Please take the class.
Yes.
You'll be a better person for it. Yeah, so what we do is we kind of instead of using integers, we actually use what are called rings,
Mhm.
where an element in the ring is basically a vector. Yeah, so it's a vector of dimension d. And it turns out that allows us to shrink the dimensions of the matrix that we're multiplying by a factor of d, both in the height and the width. So we end up with a matrix that's d time narrower and d time shorter. And
Mhm.
it turns out that further speeds up the ITI hash. Yeah, so not it's already really fast because of this
Yeah.
matrix vector product, but now we can make it even faster. It turns out
Mhm.
by using these rings, it allows us to shrink the matrix And then, of course, there's some maybe we won't get into the details here, but it turns out you have to use the magical fast Fourier transform algorithm
Yeah.
to speed up ring operations, multiplication in the ring. And then
Hmm.
lo and behold, you get a factor of d speed up in computing the itai hash. It was already fast, but now it's even a factor of d faster. Yeah. So that's kind of why we use what's called a module SIS
Hmm.
in order to speed up the compression. Now, unfortunately, the plot thickens a little bit. We're not at the end of the story in
Okay.
that once you start using itai hashes for folding, things become more complicated, unfortunately. Like if all we did
Hmm.
was just replace Pedersen with an itai hash, folding would be like 30 times faster
Hmm.
with
Hmm.
lattices compared to no to what's done with the original systems.
Hmm.
But unfortunately, the itai hash is only binding when we hash small vectors.
I
Yeah.
see.
And so remember I told you that the way we fold is we take sort of linear combination of statements, or
Yeah.
rather linear combinations of witnesses rather. Um, yeah, well, it turns out when you take linear combinations, the norm starts to grow, right? If I give you two vectors, these two vectors are low norm. If you
Hmm.
combine those two vectors together, by some linear combination, you end up with a vector with a much larger norm.
Right,
Yeah.
right.
And that's a problem. That's a
Yeah.
problem. That's a problem that we have to solve. And so what we end up doing is after folding, we have to, so the itai hash would no longer be binding if we use it to commit to a large norm vector.
Hmm.
So what we have
Hmm.
to do is we have to shrink the norm. And how do we shrink the norm? We
Hmm.
take the vector and we decompose it into smaller vectors.
I
Yeah,
see.
it's like taking a number between 1 and 100,
Hmm.
and the way we reduce its norm is we treat it as a vector of dimension 2, where each one of the components is a digit of the number, right? So we
Hmm.
take the number 81 and we think of it as a vector 8 comma 1, right? And
Hmm.
all of a sudden now it's a higher dimensional vector, but now its norm is much lower. Yeah, because instead of 81, we now have only 8 and 1 to deal with. So this is called decomposition. And so we have to decompose the vectors. And unfortunately, that's not, I wish that's all we had to do, but that's not enough, actually. It turns out we decompose and then we have to give another proof that the vectors we're committing to actually are low norm. Yeah, so this is what's called a range proof,
I see.
where I give you a proof that the value I commit to is actually in a small range. And these range proofs actually are somewhat expensive to compute. And because of these range proofs, I guess we'll talk about this in a minute. In LatticeFold, we proposed a particular range proof. It turns out that even though we're making great progress, great speed ups by using itai instead of Pedersen, so a 30x speed up, because we have to do decompositions in range proofs, that sort of eats up into the speed up. And at the end of the day, LatticeFold is kind of comparable in performance to the original Nova systems that are based on Pedersen commitments. But of course, LatticeFold is post-quantum believed to be post-quantum secure. Yeah, so there's still a benefit. Yeah, so that's kind of yeah. But the things actually get better, which we'll get to in just a second.
Yes, yeah, and that actually perfectly leads up to our next question about these range proofs and decomposition found out, because there's a non-trivial optimization in this paper, and the amount of decomposition and the amount of fan out and the degree of the range polynomial, these are influenced by the parameters b and k chosen in the paper. So how would a practitioner in real life, for example, choose b and k instance by instance or even step by step to minimize end-to-end proving time? And how does this interact with knowledge error budgeting? Is there any guidance beyond the evaluation-driven choice? So how would you choose the degree to this fan out that you would want?
Yeah, so that's actually an easy question. So
I see.
B is basically the base that we're decomposing to. So
I
again,
see.
remember
Hmm.
we had our number 81 that's like between 0 and 100, and we decomposed it into 8 and 1.
Hmm.
In
Hmm.
that case, B would be 10. Yeah, because we're
Hmm. Hmm.
decomposing at base 10.
I see.
In reality, it turns out because of the range proofs that's in the latticefold paper, it only makes sense to use base 2 or base 4. Yeah, you wouldn't go
Hmm.
beyond higher bases because the
Hmm.
range proofs become a little too expensive. Yeah.
Hmm.
And
Hmm.
so that's it. That's just yeah, that's the real answer. You either decompose it into binary bits or you decompose it into base 4 bits, and that reduces the norm to a point where we can continue folding because now we're back to low norm vectors. And that's all it takes.
I see, I see. So then moving to another question, the relationship combines evaluation and norm checks. which can be degree heavy, as you described earlier. Beyond your CCS linearization before decomposition, could degree shavers, such as like vanishing polynomial tricks or low degree lookups, or moving more of the multilinear extension work into like arithmetic intermediate representation or GKR style layer, reduce degree without reintroducing norm growth or weakening ring soundness? So, like, where would current proofs break? And yeah.
Yeah, maybe. Look, this is, I have to say,
Mhm,
this lattice folding is a fairly young area. As I said, there's
mhm,
only three papers on this topic so far. It was only introduced, what is it, last year or so.
mhm,
So it's a fairly young area. There could be definitely more opportunities for either doing norm control better than decomposition. There could be room for better range proofs. So
mhm,
yeah,
mhm,
maybe we can use other sophisticated proof systems like GKR and such
mhm,
to
mhm.
do the range proof. There's lots and lots of open questions here. I encourage everyone to get into it. It's a new area. There's probably a lot more to do, and it seems like lattice folding could play an important role in what's coming.
I see, I see. Thank you. Within the paper, you also mention various constraint systems, namely that LatticeFold functions on CCS and R1CS, which are two different constraint systems. And you show advantages for high degree CCS and parity with hypernova on degree 2 relations. For on-chain deployment, which relation model, R1CS or CCS, do you expect to dominate and why? Would it be related to market prevalence of circuits, constraint density over the cyclotomic ring RQ, verifier cost? Like, which constraint system do you believe would dominate, I suppose?
Okay, that's a salad of letters, right? So
I see.
R1CS and
Yeah.
CCS. Let's just
Yes.
expand this a little bit. So
Sure.
R1CS
Mhm,
stands for Rank 1 Constraint
mhm,
Systems,
mhm,
and CCS stands for Customizable Constraint Systems.
mhm, mhm,
All this is just a way for expressing what is the statement that we're trying to prove. Yeah.
mhm, mhm.
So you mentioned Sudoku in your example. So you
Yes.
can encode the Sudoku puzzle. You can encode it either as R1CS or as CCS. Yeah, it's
Mhm.
basically, if you like, it's a way to kind of encode computation. The maybe another way to say it is kind of it's kind of a strange programming language. Yeah, but
Yeah.
it's kind of a way just to encode computation. Yeah,
Mhm,
and the reason we use this strange way to encode is because it's very convenient to do proofs on that type of encoding. By the way, I should say this encoding, when we encode something as R1CS or CCS, this is called arithmetization. Yeah, where we take a program, we represent it in algebra effectively, and this is called arithmetization, and then we can do a proof that the program ran correctly, for example. Yeah.
mhm,
And so the difference between R1CS and CCS is R1CS only allows for quadratic constraints. Yeah. So you basically take your long computation, you break it up into a sequence of quadratic constraints, and then you verify that all the constraints are satisfied, and that says that the computation was done correctly. In CCS, we allow for higher degree constraints. Yeah, that's the difference between CCS and R1CS. And it turns out if you allow for higher degree constraints, you are able to take advantage of some repeated structure in the computation.
mhm.
If, for example, you're doing the same operation, complicated operation over and over again, then it turns out if that operation can be encoded as, I don't know, a degree 7 polynomial, then it's better to use a degree 7 polynomial than to force you to write the degree 7 polynomial in terms of degree 2 polynomials. Yeah. This is kind of why CCS has a benefit of in some cases of being more efficient than R1CS. Yeah, and so in practice, actually, people do use higher degree constraints. They don't just stick to quadratic constraints. And so the point here is lattice fold and all these lattice folding systems, they support these higher degree constraints just as well as other systems. So yeah, so you can take advantage of CCS if it makes sense.
I
That's
see, I
all it's
see.
saying.
That makes sense. That makes sense. So now we'll move on to the LatticeFold Plus paper, which was published 1 year after the original LatticeFold paper, and it claims that it has faster, simpler, and shorter proofs via a variety of techniques, such as a purely algebraic range proof, double commitments, a sum check-based transformation. Could you walk us through how each ingredient shifts the cost profile for the prover, verifier circuit, and proof size relative to the original LatticeFold scheme? In particular, double commitments, but the other such properties that were mentioned in the paper. So,
Sure, sure. Yeah, yeah. So it's probably best to just talk about what is the main benefit of LatticeFold over LatticeFold,
right.
LatticeFold Plus over LatticeFold. Yeah.
Mhm, mhm,
So remember I told you that in LatticeFold there were kind of two important components, right? Is the one is the decomposition to keep the norm low, and the
mhm,
other one is the range proof to prove that what we're committing to is in fact low norm. Yeah, and that is needed for security to hold. Yeah. So
mhm,
that range proof was quite expensive in LatticeFold, which is why we had to decompose into binary bits, and that caused quite a slowdown. So
mhm,
in LatticeFold Plus, what we do is we actually have a new range proof, which is much more efficient. It's really quite interesting in that it's a range proof that inherently uses the ring structure that we're working in. Yeah, so remember I told you that the reason we moved to modules, or maybe let's not use the word module, let's just use the word ring. It's a little
mhm,
simpler.
mhm.
So the reason we moved to rings is basically to speed up the itai hash. There was no benefit other than efficiency. Well, it turns out once we move to rings, all of a sudden we have a ring structure to work with. And in LatticeFold Plus, we show that the actual ring structure can be used to give very efficient range proofs. Yeah, which is kind of unusual, I have to say. It's kind of cool that it's not just about efficiency. It turns out we can actually do things inside of a ring that we can't do over the integers. And the example is this kind of very cute, I think, range proof. Yeah. I should say, by the way, it's not just a range proof. It turns out it's even more general. It allows us to do general table lookups. It's just a table that we're looking up in is what allows us to do a range proof. Yeah, the table would be the numbers, let's say minus three all the way to three. Yeah, so we're proving that all the elements are in that table, and that gives us a range proof. So that's kind of the main benefit of LatticeFold Plus, that we are able to use this better range proof. It turns out that implies that causes the commitments to get a little bit bigger.
Mhm.
So now we have a sequence of commitments
Right.
rather than just one for some technical reasons. And so the double commitment you mentioned is we want to have short proofs. And so what we do is rather than publish a sequence of commitments, we actually commit the commitments. Yeah, this is the double commitments.
Mhm,
So we
mhm.
compute one commitment, which turns out to be quite large, and then we commit to the commitment,
Right.
and the commitment to the commitment is small. So it's kind of a trick to make things a little smaller. That, of course, as usual, that introduces some complexities in the protocol, but that's kind of the reason why there's a double commitment. But the main benefit, the main kind of speed up in LatticeFold Plus is this better range proof, and that seems to speed up the prover by quite a bit. Actually, well, we'll talk about practicalities of this in just a minute, but there's a company that's implementing these things, and it looks like there's actually quite a performance benefit to LatticeFold Plus over LatticeFold.
I see, I see. That makes sense. So, now let's talk about LatticeFold and its alignment with Beam Chain, which is
Oh,
vision for, or I guess we could go for the other ones too, but it's a vision for Ethereum with the goal of simplifying the consensus layer while moving ZK to the core. Do you think, how would you integrate it across slot to epoch recursion, and what metrics would you use to judge it against a Stark first approach, such as proof size, latency
sure.
cost, and decentralization, I guess?
Yeah, yeah, of course, of course. I should mention though that there's a company called Nethermind that's actually
Yes.
implementing LatticeFold and LatticeFold Plus. So as soon as they're done, we'll know the exact performance numbers. So far, it looks quite good, and so we'll know exact numbers when they're done. And so it's interesting that you bring up the Beam chain, or there's actually new versions of it. But the bottom line is that Ethereum wants to move to post-quantum signatures for their consensus protocol. Today, Ethereum uses BLS. Maybe your listeners have heard of BLS. BLS has these important properties called aggregation and thresholding, which is important for the properties of proof of stake consensus protocols. Unfortunately, we don't have something as good as BLS in the quantum world, post-quantum world. And so what Ethereum wants to do is basically move to what are called hash-based signatures, which are clearly very secure and post-quantum safe. But then, in order to aggregate them, the goal to take multiple signatures and compress them into a single signature, the goal is to actually use a snark. Yeah, so you take a bunch of signatures and you snarkify them into a single proof, a single short proof, and that's how you kind of get the compression that's needed for the Ethereum proof of stake system. Um, okay, so the question is which snark to use. So you could use a monolithic snark to take like, 10,000 signatures and prove that they're all correct and compress them into a single snark proof. Or you could use folding for this. Yeah, so you can kind of fold those 10,000 signatures into a single statement and then just prove that single statement. So to me, it looks pretty cool that we can potentially speed things up dramatically by using folding here. And honestly, this is not, this is something that still needs to be experimented with. Like again, we're waiting for the Nethermind experiments to see how well this works. But this seems like a pretty interesting path for Ethereum to take going forward. Yeah. So we use folding to compress many signatures into a single statement, and then we prove that single statement by whatever prover we'd like to use.
I see. Thank you. And finally, and you briefly mentioned this with the Nevermind thing. As for builder and
Ah,
deployment questions and all, yeah, and like future research, I suppose. I guess this is all kind of combined together into the last question. What changes would be necessary for the on-chain verifier to adopt LatticeFold? And you mentioned that Nevermind they have like, and I saw their GitHub repository with like a preliminary implementation for LatticeFold, and we're optimistic about its results. But how difficult would it be to migrate those folding schemes into the current chain? And are there other future research questions that you're optimistic about relating to this field, or what does the future look like relating to companies and ideas for this project?
yeah, so it's pretty
Mhm.
exciting to see some companies actually implement these
Mhm.
systems. I think there's actually a couple who are now experimenting with this, which is great.
Mhm.
I mean, we need until we actually implement and see the performance numbers, it's a little hard to tell exactly
Sure.
where things are going. So hopefully within the next couple of months we'll have good numbers and then we'll know. I should say, there's also an interesting twist here, which is that these rings use relatively low precision, like we use 64 bits
Mhm.
primes. And so this is extremely well suited for operating on a GPU, for example. So there's kind of a
Mhm.
lot of
Mhm.
interest in actually implementing LatticeFold on top of GPUs. That should actually work quite well. I can tell you also that the rigs that we're using are very similar to the rings that are used for fully homomorphic encryption for FHE. Yeah.
Mhm.
And so if
Right.
somebody builds like an FHE ASIC to accelerate FHE, LatticeFold will also benefit from that as well. So it's pretty interesting that the hardware that's being built for FHE might actually also benefit Snark generation, which is kind of cool. So there's a lot of systems work to do here as well. In particular, this idea of GPU based folding is pretty exciting. It probably will give a dramatic speed up to folding. So there's a even if you are interested in the math of folding, read the papers. There's probably a lot more to do there. But also, if you're interested in the system aspect of folding, there's a ton of work to do in kind of getting this to really, practical speeds and such.
I see. I see. Well, that was a very interesting cryptography research spotlight. We really appreciate your time, and we are very excited to see future developments and progress on these ideas. And yeah, that was great.